Good day, everybody. In this class, we shall discuss about logic gates. The logic gates, as the name indicates, works on logic, and it uses an algebra known as Boolean algebra. The Boolean algebra was given by Boole in the middle of the 19th century, and that logic is implemented, the Boolean algebra is implemented on logic gates. Therefore, the devices or the systems like computers and digital communication systems and some control systems which are logical systems, can be built using these devices, or logic devices, or logic gates. As I've already indicated, the applications are as follows. The digital computers are implemented using logic gates. Digital communication systems, and large-scale digital systems of the kind which are different from which are other than the digital computers and digital communication systems. And it is also used in control systems. And the digital systems are nothing but some digital circuits or systems which work on logic. Strictly speaking, a digital communication system or a control system is also can be called as a subset of digital systems. And since these applications are very popular, they have been separately categorized here. The logic gates, as I have mentioned, are used to implement Boolean logic. The Boolean logic is similar to arithmetic operations, but these are, rather than arithmetic operations, these are logical operations. Well, the arithmetic operations can also be implemented using the Boolean logic. Therefore, logic gates can be used to carry out arithmetic operations. So that is the reason why the logic gates find applications in digital computers and other calculating machines. And before going into the details of logic gates, I shall discuss about the binary logic. So first I shall discuss about binary number system. The binary number system, a discussion on the binary number system is essential here because all these devices which I have mentioned, all the systems which I have mentioned here, application systems like the computers and communication systems, consists of electronic circuits, and these electronic circuits have to understand the numbers. And please note that the electronic circuits have some active devices like the diodes, transistors, and PN junctions, and so on. If you take the transistor, we know that the transistor has three states, where one is the off state, active state, the other two are active and on states. While the off state is uniquely defined, and similarly the on state is is clearly defined, the active region is a vast region in between these two. That is the on state and the off state. Now, a transistor therefore can be conveniently used in the off and on stage or cutoff and saturation stages. And these two stages are separated by the active region, and this is a vast region. Therefore, a transistor can be used between off and on states with a huge amount of margin in between. Hence, we can build electronic circuits which can understand logic states like 0 and 1 or cutoff and saturation states. That means transistor-based circuits can be implemented to understand logic levels of binary logic levels like 0 and 1. Hence, it becomes important for us to use the binary logic to implement the systems. Like the decimal number system, wherein a number like 1259 is a 4-digit number. So this 1 is a thousandths digit, and 2 is a hundredths digit, and 5 is tenths digit, whereas 9 is ones digit. And the equivalent goes like this. It is equal to 1 into 1000 plus 2 into 100 or 10 square plus 5 into 10 plus 9 into 1. So this is the equivalent of this decimal number. Similarly, we can have binary logic, and in a decimal number, please note that we have 10 distinct numbers from 0 to 9. And once you go beyond 9, we can represent it by a two-digit number, a tens digit, and a units digit, where the tens digit can again be any one of the numbers from between 0 and 9, but its position is such that that number is multiplied by 10. It's a tens digit, therefore it has a value of 10 times that, 10 times of that number. This is how it is. A decimal number system is represented. Similarly, a binary number like this is equivalent to 1 into, it is in 5th position, therefore 1 into 2 to the power of 4 plus this is a unity digit, this is 2's digit, this is 2 square, that is 4's digit, this is 8's digit, and this is 16's digit. Therefore, or 2 to the power of 4's digit. Therefore, it is 1 into, its value is 2 to the power of 4 plus 0 into, its value is 2 to the power of 3 plus next number is also next digit is also a 0. So 0 into 2 to the power of 2 here plus this digit is 1. So 1 into 2 to the power of 1 plus the last digit is 1 into 2 to the power of 0. And its value therefore is equal to 16 plus 0 plus 0 plus 2 plus 1, and that is equal to 19. So this is equivalent to a decimal number 19. A decimal number 19 in binary number system is equivalent to this. Because of binary numbers, that means there are 2 digits only possible, a 0 and 1. Once you go beyond 1, it goes into a 2's digit. It has to be 1 0, whereas where 2's digit is 1 and unit is digit is 0. For example, a binary 0, a decimal 0 is equivalent to a binary 0, a decimal 1 is equivalent to a binary 1, but a decimal 2 now is equivalent to a 1 0, because it is going beyond this number, and therefore it can be represented by a digit in the 2's position and another digit in 1's position. Similarly, 3 can be represented as 1 1, 4 can be represented as 1 0 0, it goes into fourth position. So that means, so this is a, so unit is digit, so this is 2's digit, so this is 2 squares digit or fourth digit, this is 2 cubes digit, and this is to the power of fourth digit. Like we have represented, we can represent any big number using 0 to 9, digits 0 to 9 itself. So this is a digit between 0 and 9, this is a digit between 0 and 9, 5. But it is getting its value because it is in tens position. Likewise, here any number can be represented by two digits 0 and 1. If the number goes beyond 1, so we have a higher position. For we can represent it, the once it goes beyond this, we can give a higher value to this and still represent it by numbers which are by digits which are zeros and ones itself. So this is how the binary number system is defined. Similarly, one can represent numbers by quaternary numbers using 0, 1, 2, 3 itself, and once it goes beyond 3, you will have fourth position, and if it goes beyond that, we have 16th position and so on. So number system can be with any base, and here it is a binary system, whereas this is a decimal number system. Now, in a binary number system, a number with any value can be represented only with two digits, 1 and 0. And these digits in binary number system are known as bits. These are known as bits. This is bit 0, this is bit 1. For instance, any number between 0 to 16 can be represented, 0 to 15. For instance, 15 can be represented by this number 1 1 1 1. So 0 to 15, a number can be represented by a 4-bit binary number. Now, therefore, a number with any value can be represented by a binary number of this type. It has certain positions, and in each position takes any one of these bits, zeros and ones. And this can also be viewed, a binary system has an advantage. It can also be viewed as a logical system. A 0 can be used to designate no, and a 1 can be used to designate yes, and it can be a function of yes and no's, and or it can be a function of true and false, or high and low, like this. So different physical logical quantities can be assigned to this. Therefore, we can solve logical functions like if so and so is yes and so is yes and so input is no, my decision is no. So such logical functions can be implemented using the binary number system. In fact, the logical gates are the logic gates are such logic systems. Now let us see what these logic gates are. Basically, there are three fundamental logic gates using which other logic gates can be built. So these are an OR gate, an AND gate, and NOT gate. As the name indicates, the OR gate works on the OR logic. The symbol used for an OR gate is as given here. For instance, if it is a 2-input OR gate, so this is the symbol used. It has, if it is a 2-input OR gate, it has 2 inputs and 1 output. If A or B, any one of them, or both are ones, the output is a 1. So that's what the OR logic is. So let us take all the conditions, input conditions, and let us see what output it gives. AB can take certain logic values, both can be 0, 0, logic level 0. A can be 0 and B can be 1. Well, A can be 1 and B can be 0, and both can be 1s. So if the inputs are like this, in one case 0, A is 0, B is 0, in the other case A is 0 and B is 1, and A is 1 and B is 0, and both are 1s. So when the inputs are logic, these logic cases, let us see what the output is going to be. When both the inputs are zeros, output is a 0 in an OR gate. When any one of them are 1s and or both of them are 1, the output is a 1. So that's why its name is an OR gate. If any one or both of them are 1s, the output is a 1. Otherwise, the output is a 0. So this is the logical relationship with which this OR gate works. And the table which indicates the input-output relationship is known as the truth table. So this truth table gives the function of an OR gate, 2-input OR gate. Similarly, one can have a 4-input OR gate, 3-input OR gate, or 4-input OR gate, and so on. So in which case, going by the OR logic, if any one of the inputs is a 1, or all of them are, or any few of them are 1s, output is a 1. That means output is a 0 only when all of them are zeros. So this is what the OR logic is. A Boolean expression for this is like this. In the case of a 2-input OR gate, the output Y can be expressed as A plus B. According to the Boolean logic, Boolean algebra, 0 plus 0 is a 0. It is indicated by a plus sign. The OR gate is. OR function is given as a plus sign, and according to Boolean algebra, according to that, 0 plus 0 is a 0, 1 plus 0 or 0 plus 1 is a 1, and 1 plus 1 is also equal to a 1. It's not 2 like our arithmetic operation. So that's what is the Boolean algebra. So according to Boolean algebra, A plus B is equal to Y, and that's what an OR gate gives. Now, there are a few identities which can be expressed. Now, if there are 3 input, or there is a 3-input OR gate and A plus B plus C, please note that whether you first OR A plus B and then you take the result of that and OR with C, or you take first OR B and C first and then OR with A, it gives the same result. So A plus B plus C. Or first you take OR operation on A and C first and take the result and apply an OR operation on B. So what I mean to say here is, according to this, first you take A and B, use a 2-input OR gate, and then this is the result of this 2-input OR gate operation, OR operation. And now take C here, and on these two again apply an OR operation, and you get the overall output Y. Okay, so in this operation, whether you do this first or that first, it is one and the same. Therefore, it is associative. Then A OR with B or B OR with A, it means one and the same, and you will get the same output. So this is what results from this operation. Because the truth table for OR operation is this, so naturally these are valid. It can be very easily shown that this is valid. We can easily imply this from the truth table of OR function. Another identity is, yes, as I mentioned, A plus B or B plus A is or it is one and the same. These are one and the same. So A plus A, in case you apply both same input to both, so A plus A is equal to A. That means if it is, if you're giving the same input to this also, that means it is like this. If this is going, the same input A is going to both the inputs of an OR gate. If A is a 0, it is 0 plus 0 is a 0. If A is a 1, 1 plus 1 is a 1. When you add 1 and 1, or when you OR 1 and 1, you will get a 1. Therefore, you get A ORed with A will give you A itself. And 0 ORed with A will give you A itself. Because if A is 0, the result would be 0. If A is 1, 0 ORed with 1 is a 1. Therefore, the result is A itself. On the other hand, if it is A ORed with 1, any input ORed with 1, the output is a 1. Because if any one of the inputs is a 1, output is a 1. Therefore, these identities are valid in the case of an OR gate. There is another interesting gate known as an AND gate. Before discussing about the AND gate, I would like to mention that we can build such gates like an OR gate using electronic devices like transistors and resistances. In fact, in the subsequent lectures, I'll be discussing about how to implement these gates using diode circuits and transistor circuits. Now let us discuss about an AND gate. The symbol of an AND gate, a two-input AND gate, is as given here. So it has two inputs and it has one output, C. Now the AND operation is defined like this. If this input A and B are 1s, then only the output is a 1. Otherwise the output is a 0. Hence the name AND gate. Its truth table can be given like this. Therefore, if these two are inputs C and B, so this is the output C. It can be given in a table form. When both are 0 zeros, naturally output is a 0. And as the logic goes, if both the inputs are 1s, output is a 1. Otherwise, the output is a 0. If this is 0 and this is 1, and this is 1 and this is 0, or both are zeros, output is a 0. If it is a 3-input AND gate, if A and B and C all are 1s, then the output is a 1. Otherwise, it is a 0. Similarly, a higher order, with higher number of inputs also, the AND function can be defined. So this is the logic. And the expression, logic expression that is used is, it is like a product expression. 1 into 1 is a 1, or anything into 0 is a 0. So the logic is like a product expression, whereas for the OR gate it is like an addition expression. Therefore it is designated by a product expression. A into B is equal to C according to the Boolean algebra. And that's what this truth table shows. Now let us see some identities. Like in the case of the OR gate, let us consider a 3-input OR gate. When you 3-input AND, when you first do AND A and B and then take the result and AND with C, or you first AND B and C first and take the result and AND with A and so on, it is equal to same ABC, all are equal. Because it's a product operation, then the result, once you get the result, even if this is output Y. I'm changing the symbol here, the output is Y to be with the same, to follow the same notation. Similarly, it is commutative. So AB is equal to BA. You can't differentiate between this input and this input. If you put B here and put A here, the same thing is valid. Still, the same result is valid. Therefore, it is commutative. AB is equal to BA. Now, when you apply the same input to both, that means when you apply, it's a 2-input AND gate, and so you take one input A and apply the same to both, then what we have is A into A is the Boolean expression, and the result is A. Naturally, because if A is a 0, both inputs are 0. When both inputs are 0, output is a 0. So that is valid, because if you make it equal to A, that is valid. When A is 0, there is output is also equal to A, that is 0. And when A equal to 1, we have a situation here where it is 1 and 1. For when both the inputs are 1, output is a 1. Therefore, what you are getting at the output is exactly equal to A itself. Hence, A into A is equal to A. And if it is A and A and A, if it is 3-input AND operation with all equal to A, still also the output is A. Similarly, anything ANDed with 1 is equal to, so that input A itself. Because once one is a 1, if the other one is a 1, output is a 1, otherwise the output is 0. That means what you get here is this input itself. When B is 1, output is going to be equal to A. When one input is a 0, irrespective of whatever is, when this is 0, for instance, irrespective of whatever input you have here, output is going to be 0, because the condition is that all inputs are to be 1 for the output to be 1. Otherwise, the output is 0. Hence, any input into 0 is a 0. Now, there is a logic I'm giving a logic which is a combination of both. Say A into B plus C. That means what is it we are doing? So we are taking 3 inputs A, B, C. First, if we OR B and C using an OR gate and get a partial output B plus C here, with B here, C here, using an OR gate you get B or C or B plus C. Now if we AND with A, this result with A, so this is what we get an output Y. Please note that, so this can be shown that it is equal to A and B plus A and C, or A and B or A and C. So it can be very easily shown with the help of the truth table, and because yes, it can be shown with the help of the truth table. This operation can be. Here you may also note that we can have a larger logical expression like this implemented using these gates. So in fact, it can be a much larger logical expression, and it can be represented with these gates. And if you have an electronic circuit for this and an electronic circuit for this, using electronic circuits with such logical inputs, we can get the logical output. Well, the logical inputs are to be applied in terms of voltage and currents if it is an electronic circuits, because electronic circuits can understand only voltage and currents, not the logic. Similarly, we have another basic gate known as a NOT gate. A NOT gate is a single input, single output gate. Therefore, if the input is A, so there will be there is an output which is a function of A itself. As the name indicates, what it does is it does some negation. That means when the input is at 0, it gives an output. It's negative as the output. That means 1 as the output. And if the input is a 1, it gives a 0 as the output. Hence, the truth table is very simple like this. If this input is a 1, output is a 0. And if the input is a 0, output is a 1. It gives the complement of the input. Output is the complement of the input. So that's what a NOT gate is. Now a NOT gate also can be represented using an electronic circuit. Please note that a circuit like a transistor, when the base is applied a high potential, the transistor can be made to go into saturation. That means output can be a low output. Similarly, when the input is 0, base emitter potential is 0, the outputs on the output side, you can see that no current flows and the output voltage can be large. I'll discuss about in detail in the next class. So this is what a NOT gate is. Now an OR gate and a NOT gate combination becomes a NOR gate. So which can be represented by this symbol, which is represented by this symbol. So this is a NOR gate. It is an OR gate plus a NOT gate combination. So when you use this logic, what it means is an OR of A and B. On OR of A and B, you apply a NOT operation. So this is equivalent to this. This is it. And its truth table is very simple. If this is an OR gate's truth table, in the case of an OR gate's truth table, so you get 1 here and zeros for this. Similarly, we can have an AND gate, which is an AND gate and a NOT gate combination. This is known as a NAND gate. The symbol for NAND gate is like this. This is the symbol for an AND gate. These NOR gate and NOT gate, NOR gate and NAND gate can be used as the basic building blocks for any gate, because a NOT gate also can be represented, can be implemented using either a NOR gate or an AND gate. For instance, if I connect both the inputs together and make it a single input system, in the case of an AND gate, please note that it is exactly equivalent to a NOT gate. So a 2 input NAND gate with the 2 inputs shorted and made to act like a single input, so it is equivalent to a NOT gate. Because so when these two are shorted, when you apply A and A here at the AND gate output, we get A itself, because according to the AND logic, A into the AND identities, A into A is equal to A itself. Hence, we get an A at the AND gate output. Then at the NOT output, we get A bar. That means for an input of A, you will get A bar here, or complement of A here. So that's what a NOT gate does. Hence, A NAND gate can be used as a NOT gate. Similarly, a NOR gate can be used as uh, a NOT gate by by connecting both the inputs together and making it as a single input system. So when you have A applied here, A plus A is equal to A here and A bar here. Therefore, when you apply A here, you get an A bar output here. Therefore, it can be used to act like a NOR gate. Now, any logic circuit, complicated logic circuit, can be implemented with the NAND gate and NOR gate. There is another, before going into the further details, let me give the identities of the NOT gate. The algebraic expression for NOT gate is given like this. So A bar, the output is equal to the complement of the input A bar. Now please note that if you apply two bar operations, you take the complement twice, one becomes 0 with one complement, with the other complements again becomes 1. Therefore, with double complement, it is equal to A itself. Similarly, when you take a complement of A and A, what is it equal to? It is naturally equal to 1, because if A is 1, the other one would be 0. 1 OR with 0 is equal to 1 itself. If A is 0, A bar is 1, therefore 1 plus 0 is a 1. If A is a 1, A bar is a 0, 0 plus 1 is a 1. Therefore, A bar plus A is equal to 1. So when you AND A bar and A, when one is a 1, the other one would be a 0. So they are never 1 together. Therefore, it is equal to a 0. There is another identity for A plus A bar B is equal to A plus B itself. It is an interesting result. When you have A and its complement multiplied by some other input, it is equal to A plus B itself. Why is it so? It is becoming totally independent of B itself. It is because, so these two are related. When this is already 1, irrespective of its value, the output is a 1. And when this is a 0 here, so it is equal to 0 plus B itself. Therefore, it is A plus B itself. Hence, A plus A bar B depends only on A and B, not A alone. It's not independent of B. It is dependent on B. So it depends on A and B itself, and it is equal to A plus B itself. With the help of a truth table, it can be very easily shown. There is another widely used logic gate. It can be built with the NAND gates and NOR gates, and that is an exclusive OR gate. Or rather than a gate, it is a circuit, because it is a circuit which can be built with the basic logic gates, which I have already discussed. Let us look at this circuit. The exclusive OR function is defined like this. It's a 2-input exclusive OR function, and then the 2-input function. Its output is defined like this. When A and B are the inputs, let me first give the logic symbol for an exclusive OR gate. So this is an exclusive OR gate, a 2-input exclusive OR gate. Then its truth table is like this. when it is 0 and when both the inputs are equal, the output is a 0. That means when the inputs are 0, 0 or 1, 1, the output is a 0. Otherwise, the output is a 1. That's how an exclusive OR gate is defined. That means for 0 and 1 and for 1 and 0, for both, output is a 1. It can be used for detecting the similarity between the logic similarity between both the inputs. When both the inputs are similar, that means either 0, 0 or 1, 1s, the output is a 0. So it can be used for similarity detection between the input logical values. So it can be this logic, an expression for this logic can be expressed in this form, in this Boolean algebra form, a plus b into ab bar. Similarly, it can be expressed in this form, ab bar plus ba bar. That means it is a and the complement of b ANDed and ORed with the AND operation on b and the complement of a. With the help of Boolean logic algebra, or with the help of the truth table, so AND gate and complementary, the NOT gate and the OR gate, it can be shown. So this input-output relationship can be expressed in this form. Now once the expression is known for us, we can make use of, we can get a circuit to implement this. As I have mentioned here, if you have two inputs A and B, first complement B, take A itself and AND these two to get AB bar, and take this, complement this, and these two to get BA bar, and you OR these two. So you get this output Y. And this is a logic circuit using the basic gates to implement this logic. So this is what is known as an exclusive OR gate. Now this exclusive OR gate can also be implemented by other circuit forms. For instance, here we have used, just now I showed how AB bar plus BA bar can be realized with this circuit. And similarly, this expression can also be used to realize a circuit, again using OR gates, AND gates and NOT gates to realize the exclusive OR gate. And this exclusive OR gate is also an important gate, because as it is, so this gate is used in realizing some functions like carrying out binary addition and binary full addition and half addition. I'll discuss about it a little later. Now, apart from the identities which were given here for the AND gate, OR gate and the NOT gate, that the associative, commutative laws and the other identities are valid or given, there are two other laws which can be used to minimize logical functions. I'll explain what is meant by minimization of logical functions first. For instance, a logical function like a plus b into b plus c into c plus a. This is a function of inputs a, b, c, and c. It has ORing of this input, this input, these inputs, these inputs, and these inputs, and then ANDing of them. It can be shown that it is equal to AB plus BC plus CA. Similarly, a Hughes function consisting of a few inputs can be minimized, and it can be shown as a small expression of A, B, and C. It's because to start with, when the logic is worked out, the function may be redundant, and the redundancy can be reduced by using this function. Like as I mentioned, A plus A bar B can be reduced to simply A plus B using this identity. Similarly, big functions can be reduced to small functions and they can be implemented using the logic gates so that we can efficiently implement the logic circuit. Now while doing so, there are two laws known as De Morgan's laws which can help us. So these De Morgan's laws are based on the logic that if and only if all inputs are true, then the output is true. So such logic can be expressed in two different forms. For instance, if and only if all inputs are a 1, that means all A into B into C, etc. If there are many inputs, the product of all of them, the end operation of all of them should result in a 1. Then this can also be expressed as A bar plus B bar plus C bar plus etc. whole bar. So that's because if and only if all inputs are true, then output is true. That means all inputs are true and the output is true is also valid in this particular case. Hence, A bar plus B bar plus C bar etc. whole bar is equal to ABC, the product of ABC. Its complement is as follows. If A plus B plus C, A plus etc. whole bar is equal to A bar, B bar, C bar and so on, or equivalently, if we apply another complement on this, A plus B plus C plus etc. is equal to, so A bar, B bar, C bar etc. whole bar. So this is De Morgan's law number 2, and these two laws are based on the logic that if any one of the inputs, if all of the inputs are true, then only the output is true, and if in this particular case, if any one of them is true, if all of them are false, the output is false. So based on these two logic, this expression can be formulated, and it's a law, and these can be used to minimize the logic. As I mentioned, logic functions can be used to realize circuits, computational circuits. I'll show here how a logic circuit can be used to add binary numbers. For instance, a half adder can be used to add two binary numbers of 1 bit each. A half adder uses two inputs, A and B, 1 bit binary numbers, and what it gives at the output is the sum of these two, the arithmetic sum of these two, not the Boolean sum, arithmetic sum of these two. So it gives two outputs. This is the partial sum output and this is the carry output. Please note that according to Boolean logic, according to arithmetic, 0 plus 0 is a 0, 1 plus 0 is a 1, 1 plus 1 is a 2, which is equal to 1, 0 in binary logic. Therefore, in this two output, two input system, when the inputs are added, A and B are added, so you have P partial sum and the carry here, and carry when both are 1s, the carry should be 1 and the partial sum should be 0 to satisfy this. When both are zeros, partial sum is a 0 and carry is a 0. Well, when it is 1 and 0, 1 or 0 or 0 or 1, the partial sum is a 1 to satisfy this, and the carry is a 0. So this is the logic with which the half adder works. A half adder can add two binary bits and give an output, a carry output and a partial sum output. For instance, this can be implemented. The carry output is an AND operation on the inputs A and B, and it can be seen that the partial sum output is an exclusive operation on the inputs A and B. this is the partial sum, this is the carry operation. So if you represent this as a function of the AB and this as a function of these two separately, so this is what a half adder consists of. Similarly, other logic, other such arithmetic circuits can be built using the binary numbers.